Hello everyone, my name is Melvin and this is our final project, how a computer actually works behind the screen. Computers store and process all information using bits, which are ones and zeros. Bits combine to form binary numbers which represent things like text, images, and sound inside a computer system. The ASCII table in the first image shows how letters are stored as binary codes. The second image shows how images are stored using color codes. Every pixel is represented by a number, usually in hexadecimal like FF for white, or 00FF00 for green. These color codes combine to form pictures on the screen. The third image shows 2's complement, which lets the computer represent negative numbers using bits. It lets the computer do subtraction by turning it into addition, which makes the hardware simpler. The first image shows a diagram of how a MIPS processor works by moving data between the register file, the ALU, and memory. It helps show that MIPS executes instructions in small steps like fetch, decode, execute, and store. The second image shows a load instruction where the computer takes a value from a memory address and puts it into a register. MIPS uses LW and SW to move data between registers and data memory. The third image shows two different ways computers store multi-byte values in memory. Big endian stores the most important byte first, and little endian stores the least important byte first. This image shows a small MIPS program taking two numbers from memory, adding them, and storing the result back into memory. The LW instructions load the numbers into registers, the add instruction adds them, and the SW instruction saves the answer. The picture also shows the registers and data memory so you can see how the values move through the CPU.
When we write code in C, it looks simple and relatable for us humans, but the computer cannot understand this type of code directly. So first, the compiler converts the C code into assembly language, which is a lower level language that uses instructions like add, load, and jump. After that, assembly gets translated into machine code, which is made of zeros and ones. That binary code is the only language the CPU understands. For example, the simple C statement x is equal to x plus 1 becomes an assembly instruction, a $T0, $T01, and then becomes machine code as a sequence of zeros and ones. So the whole purpose of this conversion is to turn human instructions into something the computer can actually execute. The CPU is known as the brain of the computer because it carries out all the instructions. It mainly has three important parts. The control unit acts like a manager. It tells all the other parts what to do and in what order. The ALU, which stands for Arithmetic Logic Unit, is responsible for doing all the math operations and decision making, like comparisons. Then we have registers, which are tiny but very fast storage locations inside the CPU. They hold data temporarily while instructions are being processed. So basically the control unit directs, the ALU performs calculations, and registers store the working data. Together, they help the CPU execute instructions. Computers use different types of memory, and each level has a different speed and size. At the very top, we have registers, which are the fastest but store the least amount of data. Next is cache, which is still very fast and stores frequently used data close to the CPU. Then we have RAM, which is the main working memory and holds data while programs are running. At the bottom, we have hard drive or virtual memory, which has the largest storage but is also the slowest. So as we go up the pyramid, speed increases, and as we go down the pyramid, storage increases. That's why we say higher levels are faster but smaller, lower levels are larger but slower. Moving on. Input and output is how a computer communicates with the outside world. For example, when we type on a keyboard, that is input, the input goes to the CPU where the instructions are processed. The CPU may temporarily store or retrieve data from memory, which could be RAM or cache. After processing, the computer sends the result to an output device like a monitor or speakers. This whole process from keyboard to CPU to memory and then to the monitor is how input becomes output. Computers use memory mapped I/O, interrupts, and DMA to manage this communication efficiently without always involving the CPU. Now let's see how everything we learned works together as one full system. This diagram shows the complete journey of writing code to actually seeing results on the screen. We start with C code, which is human readable. Then the compiler translates that code into assembly language, which is closer to what the hardware understands. Next, the CPU, which includes the control unit, ALU, and registers, takes those assembly instructions and starts processing them. The control unit decides what needs to be done, the ALU performs the calculations, and the registers hold quick temporary data. During this process, the CPU constantly uses the memory system, starting from registers, cache, RAM, and sometimes the hard drive or virtual memory, depending on how big or how fast the data needs to be. Finally, once the CPU finishes processing the instructions, the results are sent to I/O devices like your monitor, speakers, printers, or keyboard feedback. This is how your typed code becomes something you can actually see, hear, or interact with. So everything works together like a team. The software becomes hardware actions processed by the CPU, temporarily stored in memory, and delivered to the outside world using input-output devices.
Hi everyone, my name is George and I'm going to be going over logic gates and circuits today. And before we start, I have a quick question. Have you ever wondered how computers actually think? Well, computers actually think by using logic gates and circuits. Logic gates and circuits are the fundamental building blocks that let computers make choices, process information, and perform operations. And you might be wondering, how does all this let a computer perform all those operations and do all those complex things? So basically, at the lowest level, all computers understand is electricity. Computers don't understand what you type in, they don't understand numbers, they don't understand pictures. And you might be thinking, oh, they understand binary. Computers understand 0 and 1s. But where binary actually comes from is the flow of electricity, and they understand electricity. So pretty much 1 means electricity is flowing on, and 0 means electricity isn't flowing, aka off. And that's where binary came from. So binary isn't just some random system that someone picked, it actually matches how electricity is flowing and how electricity is behaving. And then you might be thinking, how does the computer actually control electricity? The computer controls electricity using these tiny things called transistors. I didn't put it in here, but transistors are these little electronic components that turn on and off very fast. And when you connect a bunch of transistors together, they form logic gates. Logic gates pretty much take one or more binary input and produce a binary output. And right now, I'll be introducing to you guys 3 fundamental logic gates. So starting with the AND gates. The AND gate only outputs 1 if both are 1. Similar to the AND operator in C++, where both have to be true for it to output a true. So as shown in the truth table pretty much shows you how the AND gate works. If you input 0 in A and you input B in 0, or input B is also 0, then the output is also going to be 0. If A is 0 and B is 1, then the output is going to be 0. And if inputs in A is 1 and B is 0, then the output is also going to be 0. The only way the output could be 1 is if the input of A and B are also 1. And then it's similar to like a light switch that only turns on if both switches are turned on. So moving on, we have the OR gate. The OR gate is also like the C++ operator, where only one condition has to be true in order for it to output true. So as shown here, if input A and B are both 0, it's going to output 0. But if one input is 1, then it's going to output 1. And if both inputs are 1, it's also going to output 1. So it's going to turn on whether or not, as long as one of the inputs is 1. And lastly, we have the NOT gate. The NOT gate pretty much just flips the input. So if you input a 0, you get a 1. And you input a 1, you get a 0. Pretty much just flips it. Gives you the opposite. When you connect all these gates together, you get something called a combinational circuit. These circuits don't have memory, they don't give feedback, and the output only depends on the input. Okay now, so moving on to the 3 most important combinational circuits, we're going to be talking about the decoder, muxer, also known as a multiplexer, and adders. So, starting off with the decoder. The decoder pretty much converts n input bits right here and converts it to 2n outputs, unique outputs. And there's only one output being active at one time. An example would be a vending machine. So like say you select a button, it only selects one item. And if you have 2 input bits, you can get 4 outputs, since 2 to the second power is 4. And what they're pretty much used for is to help CPUs choose things like registers, instructions, and access memory locations. So moving on to the muxer, also known as the multiplexer, is a combinational circuit that has many data inputs and a single output, depending on control or select inputs. So it's pretty much like a train track switch, and it selects the bits to decide which paths to get used. Right here we have a 4 to 1 mux, which needs to select 2 bits, because 2 bits can represent 4 choices. And it's pretty much built by the AND, OR, and NOT gates, and what's used is to choose ALU inputs and pick between immediate and register values. And lastly, we have the adder. The adder pretty much performs binary addition, and are the circuits that let the CPU do math. A half adder adds 2 bits, while a full adder adds 2 bits plus a carry in. All adders are built from the XOR and OR gates. So to add a 32-bit number, the CPU chains 32 full adders together, forming the ALU's main adder circuit. So, to sum everything up, binary pretty much gives computers their ones and zeros, transistors control electricity, logic gates make basic decisions, and combining logic gates gives you combinational circuits that are used for useful functions. And decoders, muxers, and adders are the key circuits that allow a CPU to choose, route, and compute. All this form the ALU and the control logic inside the CPU. So it's kind of crazy how a simple on and off with electricity can become logics and circuits that power how every computer runs. And that's it. Yeah, thank you for watching.
Hello, my name is Andrew, and I will be going over machine and assembly language and how the process works. Here we have an example of a LW instruction or a load instruction. It comprises of a destination register here at the beginning, the offset here at the middle, and the base address at the end. The offset is used to determine the specific memory location to access from a base address. From the data that the offset and base address load up, it is then transferred to the destination register and it is loaded in there. Heading to the next slide, we can see a diagram of how a CPU fetches the instruction, breaks it down to binary code for the computer to kind of understand, and executes the instruction accordingly. And it kind of goes in a cycle, as we can see on the top. On the bottom, we can see a diagram of how assembly language is decoded from the computer to kind of understand and execute all these instructions. So it kind of takes it to something it can actually kind of read. These are just a couple of examples of machine and assembly language, and thank you very much.